Consider the problem of computing some probability from some representation of a probability distribution. And this could be a graphical model such as a Bayesian network or a Markov random field, or a probabilistic programming language such as Problog or Blog. Regardless of the representation, we can use weighted model counting as the mechanism or the framework for that computation. WMC is a generalization of propositional model counting with applications to probabilistic inference for all kinds of models, as well as more recently to neural symbolic artificial intelligence as well. So in this simple example, we're trying to compute the WMC of this formula, and since we have two variables, the weight function is defined on 4 literals. And in order to compute the WMC, we add the weights of the models of the formula. So this formula has 3 models, and the weight of each model is defined as the product of the weights of the literals in that formula. WMC algorithms come in 3 main flavors. First, we have those that are based on knowledge compilation. So they transform the original formula from CNF to some more restrictive format, which allows for various operations to be performed more efficiently. Another option is to use SAT solvers, and the third type of algorithms manipulate some representations of pseudo-Boolean functions. So let's consider this simple Bayesian network with just 2 random variables, each of which has 2 values. And this is one of its possible WMC encodings. So even in the simple example, we're going from 2 variables to 8 variables and 17 clauses. And if we look at this instance in more detail, we can notice all kinds of redundancies. So for example, not x1 is defined to be equivalent to x2. x1 is defined to be equivalent to x3. And we have a new variable which is defined to be equivalent to each possible conjunction of x1 and x4. And this complexity comes from the requirement in the definition of WMC to put weights on literals. So while it would be a lot more simple and natural to put a weight on this conjunction, since that is not possible in the context of WMC, a new variable has to be introduced, and it has to be defined to be equivalent to these variables. And this adds a lot of clauses and variables and makes the instance a lot bigger. So in the rest of this talk, I will propose a more expressive alternative to WMC. I will talk a little bit about how one can transform WMC instances into this new format, and what kind of conditions need to be satisfied for this transformation to take place. And then I'll cover some experimental results on Bayesian network encodings. So first, let's define WMC a bit more formally. We have a propositional formula in CNF over some set of variables, and we have a weight function defined for all possible literals. And we split the variables into indicator and parameter variables, where indicator variables have both weights equal to 1. Another definition we will need is that of minimum cardinality model. So in this case, cardinality, we can consider each model or variable assignment as a subset of variables, and then cardinality refers to the cardinality of the set. And there are actually two variations of weighted model counting. The goal of weighted model counting proper is to add the weights of the models, and the weight of each model is the product of the weights of the literals in it, as we discussed previously. Another variation of WMC is the minimum cardinality WMC, where we're only summing over models that have the lowest possible cardinality. Most WMC algorithms only support the first kind, but some quite influential encodings are written for the second kind. And alternatively, instead of considering a propositional formula, we can replace it with a set of pseudo-Boolean functions. So these are functions of this form, going from the power set of the set of variables to the real numbers. And just for convenience, we restrict them to pseudo-Boolean functions that have at most 2 values. And for such functions, we can represent them very conveniently in this form, where this function is defined to return p if a subset of variables interpreted as a variable assignment entails that formula and q otherwise. Let's take an even simpler example. This is a WMC encoding of a Bayesian network with just one random variable that has 2 values. And so the encoding has one indicator variable, 2 parameter variables, and some weights defined on these parameter variables. And we can still see the same kind of redundancy, where not x is defined to be equivalent to p, and x is equivalent to q. And this is the same formula in CNF. And as we transform these clauses into functions, parameter variables disappear, and so to represent one binary variable, we only need one variable. And we end up with fewer functions than clauses. And we can keep simplifying them. So whenever we have x and not x for some variable x, we can flip and multiply the weights and merge these two functions into a single function. And so we can keep simplifying this instance until we only have one function, and the answer to that instance is then to just add 2 numbers, 0.2 and 0. And this is in comparison with the original WMC instance that had 3 variables, 5 clauses, and the answer was not immediately obvious. There are some sets of conditions that need to be satisfied in order for this kind of transformation to work. And these sets of conditions were modeled over Bayesian network encodings specifically. The first situation is quite specific. We have the negative weights of all parameter variables equal to 1, and the clauses that mention that variable define that variable to be equivalent to a conjunction of indicator literals. So this applies to some WMC encodings of Bayesian networks. And this is a more general set of conditions. This is where we have positive and negative weights always add to 1 for parameter variables. Each clause has at most 1 parameter variable, and it always appears as a positive literal. If we have a parameter variable as a clause on its own, then that is the only clause that mentions that variable. And whenever we have two clauses that can be written in the form some function implies p, then the conjunction of those functions must be false. And for minimum cardinality WMC, we have some of conditions from the ones mentioned before, but also some more specific ones. So if we take all clauses that have no parameter variables, then they all have the same number of positive, then the models of that subformula have the same number of positive indicator literals. And the smallest number of positive parameter literals that need to be added to such model of a part of a formula without parameter variables it is the same for all such models of the subformula. Now let's look at some experimental results for Bayesian network encodings. We implemented this transformation for 4 different Bayesian network encodings. The ++ here denotes that our transformation was applied afterwards. And we run each encoding in 3 different ways. We ran it with the original algorithm that was used in the paper that proposed the encoding. And then we ran it with DPMC, which is a recent algorithm that can easily support our new format. And with DPMC, we run each algorithm with and without our encoding, our additional transformation. And the numbers in the names of these encodings refer to the year of publication. So if we start with the first WMC encoding ever proposed, we can see that it runs better with DPMC than with the original algorithm, but the performance difference between applying our transformation and not applying it is virtually non-existent. The next 2 encodings are minimum cardinality WMC encodings, so they are incompatible with most WMC algorithms, including DPMC, but our transformation makes them compatible. Unfortunately, the original algorithm is still better, most likely because there are still some redundancies in the encoding that bother DPMC but not the original algorithm. And the same story applies to a slightly more recent version of the same encoding. But our transformation does have a significant performance improvement for the most recent WMC encoding, which also happens to be the best performing encoding for DPMC, and this improvement is enough to significantly separate the best performing encoding with our transformation compared to not applying our transformation, and also to separate it from the previous state of the art. So if we look more closely at the comparison between DPMC with this best performing encoding and our transformation compared to the previous state of the art, we are winning on most instances, and we are able to solve a lot of instances that were previously unsolved. The comparison between DPMC with this best performing encoding with and without our transformation is a bit more noisy, but we're still able to solve many instances that were previously beyond reach. Now, to summarize, we proposed an alternative format to WMC that works with several WMC algorithms that are based on manipulating pseudo-Boolean functions. We showed how many WMC encodings can be efficiently transformed into this new format with the same algorithm, while removing many unnecessary variables and clauses. The identified conditions for the correctness of this transformation help explain how WMC encodings operate and how they work to encode the right computation. Performance improvements were somewhat varied and seemed to strongly depend on the encoding. With the first and perhaps most basic encoding, the performance was virtually unaffected, whereas the best performing encoding was significantly improved even further. The two main directions for future work are in generalizing these separate sets of conditions into something more unified, and in applying this exact transformation or similar transformations to WMC encodings for other applications.